So, good evening. Good evening, and welcome to the first SLAC public lecture of 2015. So I'm glad you could make it. The talk today should be a very interesting one. The speaker is Michael Kagan, who's a postdoctoral fellow here at SLAC in the High Energy Physics Group. He's a member of the team of people from SLAC who were involved with the ATLAS experiment, which is one of those large experiments at the Large Hadron Collider. Michael did his undergraduate work at Michigan. He was a graduate student at Harvard, where he worked on muons, a specialty of the Boston area in the global collaboration ATLAS. He did some beautiful work on the W and Z bosons, and then came out here and joined the team of people here who are really expert on this thing called the bottom quark. And let me just tell you one more thing about this. You've all, I think most of you who know something about high energy physics, have seen these pictures of these enormous detectors, 5 or 10 stories high, which are used in the experiments at the Large Hadron Collider. But those detectors don't work. Those detectors are meticulously instrumented. And they don't work until someone has crawled over every inch of it to make sure every circuit is working. And Michael is one of the heroes of that particular campaign, both, as I say, for muons and for bottom quarks, as you'll see. Anyway, he's going to tell you about starting from the bottom and the next round of physics at the Large Hadron Collider. So let's welcome him, please.
Can you hear me? Okay, great. Thank you, everybody, for coming. It's very exciting to see everybody here, excited about the physics happening at the Large Hadron Collider. I know I'm very excited about it. I've been working there for about 9 years now. Many of you may know the Large Hadron Collider has been shut down the last 2 years, and we're starting back up this year to continue our hunt for new physics, our hunt for answers to the open questions and the mysteries of the universe. But you know, a lot of times you hear talk about the physics at the Large Hadron Collider. You hear about the big questions, the big open questions, and the big results. But you know, often you don't hear about how exactly we've arrived at those results. So I'm going to talk to you today somewhat about those results, but also the tools we use to get there. And specifically, we're going to be talking about starting from the bottom. So that's the bottom quark. So the bottom quark is one of the fundamental particles we know about. And I've been working on it in many ways in the last few years as I've been a postdoc at SLAC. So I've helped to build new detectors to identify its signature when we produce it at a Large Hadron Collider collision. I've worked on the algorithms we use to recognize its pattern in the data from those detectors, and I've worked on using it to search for new physics, things like extra dimensions of space and time. So you might not think it's very lucrative to work on the bottom quark, but some people have found a way to make it quite lucrative. You can buy your own stuffed animal bottom quark, or really any of the fundamental particles online if you are interested. But let's jump into what we actually want to talk about today, and that's the Large Hadron Collider. So the LHC is a 27-kilometer ring sitting 100 meters underground, accelerating protons up to 99.9999991% the speed of light. So that's equivalent to protons going at what's called 7 tera electron volts, or 7 trillion electron volts. And we collide them together, producing collisions of 14 trillion electron volts. Actually, that's the design. In 2012, we were colliding at 8 trillion electron volts, and in 2012 or 2015, we'll be upgrading it to 13. So what is an electron volt? An electron volt is the amount of energy an electron gains when it's accelerated across a 1-volt potential. So what's 1 trillion of those electron volts? Well, a proton going at 1 trillion electron volts has about the energy of the motion of a mosquito. Okay, so now we don't accelerate 1 proton at a time. That wouldn't be so good. What we actually do is we accelerate 100 billion of them at a time, and then that's what we call a bunch. And then we accelerate about 3,000 of those bunches going in opposite directions around this ring, and we collide those bunches 40 million times a second. Now, if you add together 100 billion protons in 3,000 bunches, each going at approximately 6.5 tera electron volts, you get about the energy of a 400-ton train moving at 150 kilometers an hour. So That's equivalent to the TGV if you've heard of the high-speed train in Europe. So very, very high energies is what we're talking about. Now, if you look at this, this ring, you see that there's actually 4 different points, 4 experiments. I work at one of them. I work on ATLAS. ATLAS is one of the large experiments that's known as a discovery machine, a general purpose detector, and its competitor is CMS, and I'm not going to talk about them at all today. There's also 2 other experiments here. One is called ELISE. This experiment studies the collisions of lead ions, and there's also LHCb. LHCb studies the rare and exotic and very interesting properties of the bottom quark. But I'm not going to talk about those rare and interesting properties. What I want to talk about is the other properties, the vanilla properties about the bottom quark that we can use as a tool to find bottom quarks in our collisions and then use that signature of a bottom quark to hunt for new things. So just to give you an idea, this is what it looks like underground in the LHC. These blue pieces of metal here are actually the magnets bending the protons around the ring. So just to give you an idea, this is kind of how the Large Hadron Collider works. We start by accelerating the protons a little bit at a time through different accelerators. First the booster, then the proton synchrotron, eventually to a bigger accelerator, to the super proton synchrotron, and eventually we split the protons. We split the bunches in opposite directions. They move around the ring, getting accelerated all the way up to the collision energy. We zoom in underground. We can see the blue magnets here. Inside of these, there's 2 beam pipes where the protons are flying around at nearly the speed of light. We'll zoom in. Now you can see a proton here flying around with what's known as quarks, the constituents of the proton jumbling around. And as we see the 2 protons coming in, suddenly this is one of the 4 major experiments. This is ATLAS. And the 2 protons will come in and collide. And we'll zoom in past all these different transparently colored objects, and suddenly we see this collision occur, and the debris of the collision flying outward. Now each of these different transparently colored objects, that's a detector. That's a different kind of detector. Each one measures the properties of different kinds of particles, and they're organized essentially as onions. So we have layers of onions of different kinds of cameras that essentially look for different kinds of particles. Now, we do these collisions 40 million times a second because each time we collide, something different happens. Sometimes, very rarely, something like 1 in 10 billion or 1 in a trillion, something really interesting happens, like we produce what's known as a Higgs boson. So in order to be able to produce those Higgs bosons, we need to collide the particles together many, many, many times. So how does this all work? Well, it all works based on an equation I'm sure you're all familiar with, E equals mc squared. Energy has some equivalence. Energy is in some way equivalent to mass when you multiply it by the speed of light squared. So the other way to think about that is energy can be converted into mass. If we take 2 protons, we accelerate them to very high energies and we smash them together. Although the protons have a low mass, when we smash them together with high energy, we can produce a very massive object, a very heavy thing, something like the top quark, which is 175 times heavier than the proton. This also gives us a convenient way to talk about mass. Because there's an equivalence, we can talk about mass in terms of energy. So you'll very often hear me say something like, the proton is 1 giga electron volt, 1 billion electron volts. So that's essentially the energy of the, the proton is 1 giga electron volt, and that's the energy of the mass of the proton. Okay, so we collide particles together at very high energies so we can produce very heavy particles. And these collisions are very similar to the kinds of collisions that occurred very early on in the universe. The universe was very hot. The average energy of the particles was very high, and when they smash together, they can produce very heavy particles. So when we smash together particles at very high energies at the LHC, we're essentially testing the kinds of collisions and interactions and particles that could be produced early on in the universe. In fact, CERN, it's right here. If you trace it down, it turns out the kinds of collisions are equivalent to what was happening around 1 trillionth of a second after the Big Bang. So let's get back to the fundamental particles. We know what we're trying to do. So the bottom quark is one of those fundamental particles. But there's actually a whole set of them. And this whole collection of particles, as well as the way that they interact with each other, that's known as the Standard Model. Now, this is very similar to something you are probably familiar with as well, the periodic table. The Standard Model is essentially the periodic table of fundamental particles. So let's talk a little bit about the different particles that we have. So first we've got what's known as the leptons. So the leptons includes the electron, which circles around atoms. It's a very common particle, you've heard of it. But it also has heavier cousins, the muon and the tau. Now the muon you may have heard of, it's a cosmic ray particle. These come streaming down from space. And the tau is even heavier and very unstable. And then there's the siblings, the muon, or the neutrinos. Now the neutrinos are extremely light and they don't really interact very much at all. In fact, they can go through the entire Earth without interacting with anything. So I won't really talk about these much today. They're very interesting particles and an important part of the Standard Model, but we'll only mention them briefly a little bit later. We also have the quarks. So these are differentiated from the leptons because they interact with each other via what's known as the strong force, which we'll talk about in a moment. Now the up and the down you may not realize, but you encounter these all the time. These up and down are the particles that make up the proton and the neutron. But they too have heavier siblings, the charm and the strange quark, as well as the top and the bottom. So the bottom is what we'll be talking about a lot today, and the top is the heaviest particle, the heaviest fundamental particle that we know about. Now, these particles are organized such that the lightest ones are on the left and the heavier ones are on the right. So we'll talk about why that's important in a little bit. So in addition to these particles which make up what we call matter, there's also the force carriers. These are the particles that are responsible for transmitting the information about forces. So the photon is the force carrier for the electromagnetic force. The electromagnetic force is what's responsible for electric fields, magnetic fields, electricity, something you're familiar with, or things you're definitely familiar with. And the way this works is when you have two electrically charged particles, like two electrons, when they push and pull on each other, what they're actually doing is sending photons back and forth to each other. And that photon is transmitting the information about that push and pull. And that works. This is exactly what happens with the other particles as well. So for instance, we've got the gluon. The gluon is the force carrier of the strong force. And the strong force is what holds together atomic nuclei. It's also what holds together protons. So in the proton, we've got two up quarks and a down quark. And we've got gluons being sent back and forth between these quarks, holding it together. And also the other fundamental particles made of quarks, like the B meson here is made up of a B quark and an up quark. In fact, all of these kinds of particles that are made up of quarks, they're collectively known as hadrons, particles composed of combinations of quarks. In fact, the strong force is extremely strong. It's so strong that quarks can't even exist on their own. As soon as they get produced, they very quickly try to find another quark to bind with and neutralize essentially the strong force charge. Now we also have the weak force. The weak force has the force carriers known as the Z boson and the W boson, and is responsible for things like radioactive decay, as well as the decay of many of those hadrons I mentioned to you on the last slide. And you notice here, you've probably heard many times there are four fundamental forces, and I didn't list one here. It's one we're all familiar with. It's gravity. So gravity is predicted to have a force carrier called the graviton, but what we know, gravity is responsible for the motion of the celestial bodies, but it turns out it's extremely difficult to understand gravity at the quantum mechanical level, at the level of how two particles interact via the gravitational force. It's actually a big open question in physics. It's what things like string theory are trying to solve. Finally, we have the Higgs boson. This is a particle you've probably heard about very recently. It was discovered in 2012 by the ATLAS and CMS experiments at CERN. So this is a picture of the auditorium where, and one of the lectures was going on where they were unveiling the results. Actually, some of the SLAC students were there. I think Katie, who's sitting right over there, she's here in the green shirt, and Max, don't know where he is right now, but he's unfortunately just off the bottom of the slide. So this was really a fantastically interesting time. I unfortunately wasn't able to attend. I was writing my thesis, but I heard about the huge lines that were sitting outside the auditorium just waiting to get in. Now, I did stay up late to listen to it, and I was really shocked and amazed at how these two experiments, ATLAS and CMS, they did an extremely good job of not talking to each other, not telling each other what they found, so that we wouldn't bias each other. And then when we both unveiled results that showed we found a particle with approximately the same properties, approximately the same mass, all consistent with the Higgs boson, it was incredibly convincing that, CERN had really discovered the Higgs boson, with the final piece to the Standard Model that we've been searching for decades. And in fact, in 2014, Peter Higgs and François Englert, the physicist who predicted its existence, actually won the Nobel Prize. So what exactly does the Higgs boson do? Well, the Higgs boson gives mass to the other particles by interacting with them. So that, you might be wondering what that means. Okay, so imagine the Higgs bosons are like these politicians in a room. So if I walk into that room, nobody is going to pay any attention to me. I'm going to be able to walk through without any trouble. But if someone famous walks in, someone, for instance, like Margaret Thatcher, Well, every politician in the room is going to want to interact with her, talk to her, making it harder for her to move around in the room, giving her a sense of inertia, making that whole grouping of Margaret as well as all of those politicians kind of, it's one object with a lot of mass. And so that's essentially how the Higgs boson gives mass to particles. So Margaret Thatcher would be something very heavy, like a top quark, and I would be something very light, like an electron. This is a British cartoon, that's why, Margaret Thatcher. Okay, so you may have noticed that there's a lot of these particles that we kind of don't encounter very much on an everyday basis. The up and down quark make up the proton and the neutron. The electrons cycling around atoms, and the photon is responsible for light. But what about all these other particles? Well, it's very important that they're very heavy. And we have these forces that exist that allow particles to interact with each other. The other thing that can happen is because particles can interact with each other, heavy particles can actually turn into other lighter particles. They can decay spontaneously into lighter particles. So this is what's known as spontaneous decay or particle decay. So here we've got a muon, which decays spontaneously into an electron and 2 neutrinos. So this is why we don't see the heavy particles. They decay into the lighter stuff, and it's the lighter stuff that ends up sticking around in the universe, or on Earth. So you might ask, how long do these different kinds of particles exist? Well, there's a few different categories. We've got the stable particles, like the electron, the photon, and the up and the down quark when they're in a proton. We've got other particles that are metastable, and that's where the bottom quark sits, as well as the charm and the strange quark and the muon and the tau. So these are metastable, meaning when they're produced, they have a lifetime, they come into existence, and they exist for around 1/1,000,000th to 1/10 of a trillionth of a second. So that doesn't sound like a very long time, 1/10 of a trillionth of a second. But as we'll see later in the slides, to a particle physicist at the Large Hadron Collider, 1/10 of a trillionth of a second is nearly an eternity. So then we have the really heavy particles, like the top quark, the Z boson, the W boson, and the Higgs boson. So these are extremely short-lived particles. They live less than 1/1000,000th of a trillionth of a second. That's less time than it takes light to travel across the radius of an atomic nucleus. So you might be asking how we could possibly find such things at the Large Hadron Collider. Well, the key is that they decay into things we can see. So here we have a top quark which decayed into a W boson and a bottom quark, and our W boson decayed into an up quark and a down quark. Now it turns out we can identify the signatures of these quarks, of these different quarks at the Large Hadron Collider experiments. We can also identify signatures of B quarks at the Large Hadron Collider experiments. And the physics of the Standard Model tells us how, once we've measured the energy and the momentum of these two particles, these two up and down quarks, it tells us how to add that energy and momentum back together and measure the properties of the W boson. So then we can get the energy and the momentum and the mass of the W. Now, if we add the W with the bottom quark, then we have the top quark. We can add together those properties and then estimate the energy and the mass and the momentum of the top quark. So by looking for these decay products in our detectors and then reconstructing our way backwards, we can measure what's happening with the top quark, what's getting produced directly in our collisions by studying what they decay into. So you might be thinking, well, we found all the Standard Model particles. That's it. We're good. We're done. Well, the Standard Model in some sense is just the tip of the iceberg. There's a lot of open questions left in particle physics. How does quantum gravity work? What's dark matter? Are there more than one Higgs boson? Why are the neutrinos so light? Are there extra dimensions of space? There's many, many open questions. And it turns out, as I'll show you, many of these questions can be studied, or we can try to answer them using the bottom quark as a tool to go about answering these questions. So let's start with the Higgs boson. So the Higgs boson was recently discovered, and we're still trying to study its properties to pin down if it really is a Higgs boson. Does it behave exactly like we predicted? So we can predict how the Higgs boson decays. It can sometimes decay into W bosons, sometimes into Z bosons, sometimes into taus. And actually 57% of the time it decays into 2 bottom quarks. But this is just what we predict. We've only measured a few of these. Here on blue on the right, these are the few decays that we've measured the Higgs. But 57% of the time it's predicted to decay into bottom quarks, and we haven't seen it yet. It's still an open question whether most of the time, most of the Higgses that we produce, what are they doing? If this actually isn't 50%, 57%, it's more like 50%, well, that other 7% might be completely new physics we didn't expect at all. So measuring how the Higgs decays and measuring all these Higgses is fundamental to understanding if we really understand the Higgs boson. So we must understand the Higgs decay to 2b quarks, and therefore we must understand bottom quarks at the LHC. So the bottom quark is vital for understanding the Higgs boson. What about the top quark? So on this slide, I've got different circles where the area represents the mass of the particle, and the ratios here are approximately correct. Something that should jump out at you immediately is that the top quark's mass is enormous. It's much, much more massive than any other fundamental particles, and we have no idea why. Maybe there's more Higgs bosons. Maybe there's new physics that's contributing to the top quark mass. Maybe there's other particles that are interacting with the top quark that we haven't seen yet. What we need to do to answer these kinds of questions is study the top quark. And because we know how the top quark decays to a W boson and a B quark, by studying bottom quarks, we can gain access to studying top quarks and thereby study, for instance, why the top quark might have such a heavy mass. But that's not all. There's more than just the Higgs boson and the top quark. We have more exotic things that you may have heard of, like dark matter. So we look out in space and we look at the rotation curves, the velocity of stars and galaxies, and they seem to be spinning too fast. And that gives us evidence that there's some other matter out there. Here we've got what's known as the bullet cluster, where two galaxy clusters smash together. In red, you can see the light given off by the kind of standard model matter, the ordinary matter that we know about, and it's kind of smashing together in what looks very much like a collision. But there also seems to be a bunch of other matter that flew right through the collision without interacting very much. And that's what we believe is dark matter. This is one of the very convincing signs that dark matter really exists. Now, there's a lot of theories these days that there's a lot of interest in the theoretical possibility that dark matter interacts preferentially with heavy quarks, like top quarks and bottom quarks. If that's true, then we can study it at the Large Hadron Collider. If we look for bottom quarks, at the same time, we can look for dark matter. And so using bottom quarks may give us access to a way to search for dark matter. We also have even more exotic things like extra dimensions of space. So here's a model that's gained a lot of interest in the last years, where, for instance, here, this plane on the right-hand side, that's what imagine that's our four-dimensional space-time. That's where we live now. And we're connected to another space-time over here by this fifth dimension. What's very interesting about theories like this is you can play with gravity. You can put gravity on one side of this fifth dimension, and it decays. Its strength decays across this extra dimension. It gets weaker. This gives us a way to understand why gravity is so weak, and a way to access what might be a theory of quantum gravity. So these are very interesting models of extra-dimensional physics. And what's very interesting is the heavy particles that exist in this fifth dimension, they often decay to top quarks, and they often decay to Higgs bosons in our space. So suddenly, we've got extra-dimensional physics that's decaying to tops and Higgses, and then those decay to bottom quarks. So again, bottom quarks give us a way to study extra dimensions and search for signs of new physics. So maybe we should talk a little bit about the bottom quark, because it's really vital in a lot of these incredibly interesting searches. So first of all, quarks were studied. Quarks were discovered here at SLAC in 1969 by smashing electrons into protons, and we realized that the proton wasn't just a block, it wasn't just a sphere, there was some interesting structure inside of it. And not long after we discovered quarks, two physicists, Kobayashi and Miskawa, realized that some of the properties of those quarks that we were studying didn't really make any sense. And the only way that we could make sense of them is by predicting that there was another particle. 4 years later, we found that particle at Fermilab in Chicago. And as soon as you find a new particle, what's the first thing you do? Well, you try to measure its properties. So actually, the bottom quark hadrons, those combinations of quarks that have include bottom quarks, well, we measured the lifetime of those hadrons for the first time here at SLAC in 1983. And in fact, the properties of the bottom quark have turned out to be so interesting for exactly the reason that these two theorists predicted and eventually won the Nobel Prize for predicting its existence, that in the late 90s and the 2000s, we actually studied bottom quarks very, very specifically. We produced bottom quark factories tuned to produce many, many, many bottom quarks. For instance, the Babar experiment here at SLAC was one of these bottom quark factories. And that continues today at the Large Hadron Collider with the LHC experiment. Now, we're not going to talk about these properties. We're mostly going to focus on the lifetime and some of the other properties about what bottom quarks look like when we produce them at the Large Hadron Collider, so that we can find them and use them to search for things like top quarks and Higgses. So imagine we smash two protons together. Here's our collision, and a bottom quark comes out. Now, the strong force is so strong that this bottom quark, before it even travels the distance of a proton's radius, that's that's 1,000th of a trillionth of a meter. Before it even travels that distance, it starts radiating it off gluons. It starts spewing out strong force radiation, trying to neutralize that strong force. And that radiation then splits into more quarks. Suddenly we get this soup of quarks and gluons and radiation that gets produced. And this is what's essentially happening every time we produce a bottom quark. And as soon as that happens, well, these quarks start interacting with each other, and they start interacting and neutralizing the effect of that strong force and combining into hadrons. So we produce one quark, and suddenly we have this spray of hadrons coming out, this spray of combinations of quarks. So here we can see 4 of them, but often there's more, 4, 10, 20. And this is what's known, this collimated spray of particles is what's known as a jet. Now, any high energy quark that you produce will behave something similar to this. They'll produce what's known as a jet, collimated spray of particles. So now that we've produced our B hadron, we know that it only exists for a short period of time. So the average lifetime of a particle is how long it exists before it decays. So our bottom quark was produced at high energy. How far is it going to move before it decays? Well, the lifetime of a bottom quark, or bottom meson, or a B hadron, bottom quark hadron, is something like 1 trillionth of a second. Speed of light is around 3 times 10 to the 8 meters per second. So distance equals velocity times time. We multiply them together, we get half a millimeter. So we've gone from some particle that lives for a trillionth of a second, traveling now a half a millimeter. That's a macroscopic distance. That's actually something that we can measure with our detectors. So this is why a trillionth or a trillionth of a second is like an eternity to physicists, because it produces particles that live long enough that we can observe them with our systems. Now, if you've studied special relativity, you may not be very happy with me right now. I've ignored special relativity in this equation. And it would correct this equation by about a factor of 10 or 100. So bottom quarks and hadrons would actually live for something like a few millimeters or even centimeters before they decay. So now we're really talking about very large distances that precise detectors can observe. And how do we do that? Well, so we have our jet that's been produced, our bottom hadron flies away, and then suddenly it decays. It splits into its decay products, the lighter particles that it decays into. And so how do we find the B hadron? Well, we see this very interesting property, that there's a bunch of particles emanating from a point that's not the collision point. This is a few millimeters away from the collision point. So if we search for particles that don't seem to be consistent, that don't seem to have originated from this collision, and we have a bunch of them, suddenly we have this secondary point of production of particles, what's known as a secondary vertex. So this is exactly the kind of feature that allows us to find bottom quark hadrons, and allows us to separate them from the kinds of jets that we produce by different kinds of quarks. So specifically, a typical jet from an up quark has all the particles coming from the collision point. A typical jet from a bottom quark would have some of the particles coming from the collision point and some coming from the secondary vertex. And so this feature, this secondary origination point, the secondary production point, is exactly what we need to find in our detectors in order to identify that we have a bottom quark jet instead of an up quark jet. And we can do that at ATLAS. So ATLAS is the experiment I work on. It's a huge experiment. It's 46 meters long, 25 meters high, 25 meters wide. It weighs 7,000 tons. It's got 3,000 kilometers of cables connecting to the 100 million electronic channels measuring all the different particles as they pass through these different layers of detectors. And that amounts to about 300 megabytes of data per second and about 3,000 terabytes of data per year. So now, this detector itself is composed in many different layers. Those onions we saw before, these are the different layers of the onion. And at the very outside, we have magnets which bend particles so that we can measure their trajectory. We can measure the curvature of those trajectories and thereby measure their momentum. To give you a more realistic picture here, you can see those magnets on the outside. You can see the center of the detector as it's being inserted. And you can see a physicist here on the bottom to give you a sense of scale. And every once in a while, they let me in there too. Yeah, very fun to get down into the experiment. And not only is this an enormous experiment physically, but it's also an enormous collaboration. 3,000 physicists from nearly 40 different countries that are all collaborating to keep the detector running, build new components of the detector, store all of this data, analyze all this data, and present the results to the outside world. So it's really one of the biggest experimental collaborations I know about, and might be the biggest one in the world, in fact. So how do those different layers of the onion work? Well, each of those different layers is designed to detect a different kind of particle. So at the very bottom, we've got what's known as tracking detectors. So as particles pass through them, they deposit very tiny amounts of energy, but these detectors know very, very precisely where that energy was deposited. So we get a bunch of points in space, and through those points, we can draw trajectories, draw lines, and trace back where they were going and how much they curved in the magnetic field. And we'll talk about that a little more in the later slides. After this tracking system, we've got what's known as a calorimeter. So these are devices which stop things like electrons and photons and measure their energy. Outside that, we've got the hadronic calorimeter that stops those hadrons we've discussed and measures their energy and direction. And then you've got the muon system, the muon spectrometer, because muons don't interact very much with the rest of the detector, so they fly through, and then we've got more tracking detectors, more very, very precise systems where the muon deposits a small amount of energy, but we know exactly where it went. There's one other particle here, the neutrino, the one I said I wasn't going to talk very much about. Well, now I'm going to talk about it a little bit. So the neutrino gets produced, and it flies through the whole system without interacting with anything. So you might think there's no way to see it, but in fact, when we collide two protons, all the energy, all the momentum is along that beam, along the direction of the collision. There's no energy or momentum emanating perpendicular to the beam. But as you've heard of Newton's third law, for every action there's a reaction. That's actually a simplified version of what's known as conservation of momentum. There was no momentum coming away from the collision before we collided, so all the momentum after we collide has to sum up to zero. It has to balance itself out around the detector. And so if we see an imbalance, that tells us that there was a neutrino, and we can measure how much that imbalance was, and that tells us how much energy the neutrino had, or something maybe more exotic, like dark matter, which also doesn't like to interact with our detectors. Now, we'll focus on just one of these detectors today, the pixel system. Silicon pixel detector. This system is about 1.5 meters long, about half a meter tall. It's also organized into onion layers. There's 3 different layers of pixel detectors organized in a ring so that when particles emanate through, they pass through several different pixel detectors, and we can measure several different points in their trajectory, allowing us to create, to measure its path. Now this system is composed of 80 million pixels, so 80 million electronic channels measuring those positions of particles, and it's composed of about 17,000 individual pixel detectors. So here's what it looked like while we were inserting it into Atlas a few years ago. So let's look at Atlas. This was the side view of Atlas that we saw before. Let's zoom out and come around from the side and try to get a better view of what that silicon detector looks like inside of our experiment. So we peel away the outer layers, we're zooming in. Here are the calorimeters, these are the calorimeters. Here are the other systems of the tracking detector. You can see a person there for a sense of scale. This is about a meter in radius. So we peel away those outer layers. We see under the transition radiation detector was a semiconductor tracker, all different kinds of detectors measuring positions very accurately. And then we zoom in, we see the beam pipe here. This beam pipe is about 5 or 6 centimeters in diameter, 6 centimeters in diameter, and we can see a fly going through the center to give you a sense of scale of how small this is. And each of these green blocks, green squares, organized in this ring around the direction of around the beam pipe, those are individual pixel detectors. You can see them maybe a little more clearly here. We'll zoom around. You can get an idea of what the structure holding this in place is, all so that we can zoom in and eventually take a look at one of these individual pixel detectors. Okay, so that's one pixel detector. So let's break that down. The pixel detector is essentially 3 components. This green component, this middle, I guess it's kind of blue here, and then a gray component. The green component is what connects the pixel detector to the outside world. We've got thousands of computers analyzing the data being produced by the collisions, and we need some way to talk to the outside world. That's what this green piece does. In the middle here, we've got the silicon sensor. That's a slab of silicon with around 40,000 pixels on it. And every time a particle goes through, it deposits a small amount of energy on one of those pixels. We'll see how that works on the next slide. Now that energy gets produced in the form of electrons, and those electrons need to be read out, and they need to be digitized, turned from energy into a digital set of ones and zeros, and then sent out via this green electronics to the outside world. And that's what these they're called FEs, front-end electronics, do. They connect to this piece of silicon, actually every single one of those pixels, each one of these pixels, which is 50 millionths of a meter by 400 millionths of a meter, every single one of those pixels is connected to a piece of electronics through what's known as a bump bond. It's a small piece of metal. So what happens when a particle goes through one of these detectors? Well, a particle flies through, and it knocks electrons off of the crystal structure. And those electrons drift because we put this piece of silicon at high voltage. They're producing an electric field, allowing the electrons to drift. And as they drift up, they produce a small current. Moving electrons is current. So you get a small current in each of these pixels that we can measure and eventually turn into a digital signal. And this all happens in 20 nanoseconds. That's 20 billionths of a second. Okay, so what does it look like when a particle goes through one of these detectors? Well, it doesn't necessarily go through directly one pixel, and sometimes those electrons, they diffuse a little bit, they deposit energy in a few of the different pixels, so you get something like this. And I want to compare that to a typical digital camera image, because this sounds a lot like a digital camera. Now, the first thing you notice is the picture on the left is in color, and the picture on the right is in black and white. That's pretty much irrelevant for the discussion today. So if you're interested, I can tell you about how that works. But let's compare the black and white images. This is the intensity of the light that came in, and this is the intensity of the energy that was deposited by the particle. One thing you notice very quickly is that on the right, there's just a very small number of pixels that have any information in them when a particle goes through, and it's pretty typical that in about 10,000 pixels, you get about one particle per collision. Now, on the left-hand side, every single pixel has captured some light. So this may be a 10 megapixel, 10 million pixel image. 10 million pixels have information. On the right-hand side, 5. But we have to read those 5 pixels out 40 million times a second. On the left-hand side, for our digital camera, we only have to take a few pictures a second. That's typically what you would do. And so digital cameras have lots of data, but at a very small rate, and the pixel detectors on Atlas have a very small amount of data at a very high rate. Now keep in mind, this was just one of our pixel detectors, and we've got 1,700 of them. So it actually ends up being quite a lot of data, even though an individual pixel detector just has a small amount. But this really drives the design of what the silicon detector, what the electronics should do, and how they should operate in these kinds of environments. So how do we use them? Well, we've got our collision point here in gray is our beam pipe. Particle comes out and it flies through the 3 layers of the pixel detector depositing energy. Here in red is the energy, and we can draw a line through those energy deposits tracking the direction of where the particle went. Now, you notice a few things here. One, we didn't get an infinitely small or infinitely precise measurement of where the particle went. It has some spread, some small area where the energy was deposited. And if we want to draw a trajectory, well, we want to be able to draw a trajectory as precisely as possible. But in fact, there are many trajectories that could have gone through these 3 red circles, these 3 areas from which we know energy was deposited. And this kind of gives us the kind of region of where the particle went, the error cone, the set of uncertainty about where exactly this particle came from. So as we try to trace our way backwards from our closest detector back to the collision point, we see that there's actually quite a large spread of where the particle could have come from. So what happens when we produce a particle like a bottom hadron that splits in 2 or 3? So here it splits in 2, and we have the 2 particles emanating from the secondary vertex and flying through the different detectors. Then we draw we trace our trajectories back through those points, and we see that they appear to cross. But in fact, we have to be very careful. We know that we don't know exactly where the particles went. So if we look at all the different trajectories that were possible, if we look at these error cones, we see that there's actually an overlapping region between the possible trajectories of these 2 particles. What's interesting here is that trajectory actually overlaps with the collision point. So to the best of our knowledge, we have no idea whether these 2 particles came from the collision point or perhaps from somewhere else, from somewhere at some distance away from the collision point. But if we can make our detectors more precise, if we can make these red circles smaller, then those error cones will shrink, and that overlapping region will shrink, and suddenly we'll see that the region for which these 2 trajectories come from seems to be different from the collision point. It seems to be not consistent with the collision, and that's exactly how we find secondary vertices, and exactly how we find B-quark hadrons at the Large Hadron Collider. But it's not quite this simple, because they're produced in jets. So we have all these other particles flying about, complicating the situation, confusing us, making it difficult to figure out which particles came from where, and to accurately measure this overlapping region. So the better we can build these detectors, the more precise we can build these detectors, and the more precise we can measure each of these trajectories, the better we can find exactly where these two particles came from. So we can actually do this. This is a collision from Atlas, actually an old one from 2009. We have here in blue all the particles emanating from the collision point. We have our 3 layers of the pixel detector. Each of these black points is where one of these particles went through. And if you look on the right-hand side, there's this set of purple lines. And these purple lines seem to be originating from a point a few millimeters away from the collision. And this is exactly what a bottom quark hadron looks like. This is, in fact, one of our early bottom quark jets. So we found the bottom quarks. We know how to do it with our detector. What do we use it for? Well, once we can identify them, we can use them to search for other things. So here we're going to look at a collision that produced 2 top quarks. We know each of the top quarks decays to a W boson and a bottom quark. And then on one side, the W boson will decay to an electron and neutrino. That's possible. And on the bottom, it decays to an up quark and a down quark, producing jets. So this is actually what we see on the top and bottom of this image. So here we have the electron. It's actually coming from this colored line here, flying through the detector. We've got our bottom quark jet on the top, colliding with the different layers of the detector here. We've got what's called this dashed line, what's called missing energy. That's the missing energy from the balance of all the energy around the detector. That's the sign, the signature of a neutrino. Here's the neutrino here. On the other side, we've got these 3 cones. It's actually overlapping of the bottom quark jet as well as the other 2 jets. If you kind of rotated this image around to the side, you see that they're not overlapping, but they're extended along the detector. But we know how to then add things back up. So once we measure the up and the down quark jets and the bottom quark jet, we can add them all together and we can look at the properties of the top quark. And now, what's the most important property of the top quark? Well, if you want to find a top quark, it better have the mass of a top quark. So what we can do is we take a lot of collisions, and each time we see some signature like this, where we have an electron, neutrino, 2 bottom quark jets, and 2 other jets. A lot to say. Once we have that signature in a collision, well, we can measure the top quark's mass and see how many different collisions produced a top quark with a given mass. So that's what we have here. On the x-axis is the top quark candidate's mass. On the y-axis, how many of those collisions produced one of those top quarks. And what we see here is a few different colors. In the black data points, that's our data. In white is what the standard model predicts the top quark to be, and we can see this very sharp peak right at about 175. That's the mass of the top quark. This is exactly what it looks like when you have a particle. It's a peak of a bunch of collisions that had particles produced at about the same mass. But we also see these other colors. These are other different kinds of collisions that didn't have top quarks in them, but had the same signature in a detector, and we couldn't really separate out. And you can see very clearly that the top quark stands out tremendously above all these other backgrounds. But we can go one step further. Our collision had 2 top quarks in it, so let's add those 2 back together and see if something heavy, something new, produced those 2 top quarks. So this is exactly what we did here. Here we have the mass of the 2 top quarks put together on the x-axis, and on the y-axis is the number of collisions. In blue is all the stuff that the standard model predicts, all those top quarks from the standard model. And in red here are 2 different models of new physics. One is a heavy new Z boson, and the other one is a heavy new graviton, which actually predominantly comes from a 5th dimension. And, well, unfortunately, we don't see a peak jumping out on above our blue distribution here. The data is in black. So unfortunately, we didn't find new Z bosons or new heavy gluons, but we were able to limit that those new particles didn't get produced with a mass less than about a TeV. Now, this isn't the only kind of search. Just looking for top quarks isn't the only thing we do with bottom quarks at the Large Hadron Collider. We can also look for new force carriers here, looking for force carriers, a new heavy W that decays to a top quark and a bottom quark. We can look for dark matter. Here, a bottom quark was produced at the same time, or we're looking for bottom quarks produced at the same time as 2 dark matter particles. And we look at the imbalance in the event, and we measure how big was that imbalance. And in red is the signature of what that imbalance would look like if we had extra dark matter. And in green is what we predict from the standard model. And unfortunately, the data points here lie directly on our prediction. So we didn't find dark matter last year, but hopefully next year. We can also look for Higgs bosons. So I said we haven't been able to find the Higgs boson decaying to two bottom quarks. So here is where we search for Higgs bosons, looking for 2 bottom quarks. We add those 2 bottom quarks together, and we get this kind of this kind of very colorful set of things. So we have this very small blob here, this very small smidgen. That's what we predict for the production of Higgs bosons by the Standard Model. And all this other colorful stuff, those are all the different backgrounds that produce a very similar signature in our detector. And so the problem with finding Higgs bosons is that there's a very small signal on top of a very large background. And so in order to be able to really find that next year, or this year, and hopefully over the coming years, we need to very precisely understand these bottom quarks and separate out this tiny Higgs signal from all these other backgrounds. Now, just because we haven't found the Standard Model production of Higgs bosons doesn't mean we can't look for other things that have Higgs bosons. For instance, here's a theory. Here's a model where we have two protons collide. They produce a graviton that's coming from that extra dimension we saw in that model earlier. It decays to two Higgs bosons, which then each decay to bottom quarks. We end up with 4 bottom quarks in our event, really a spectacular signature. Now, if we add up all these bottom quarks, we can look at the mass of that combination and see if we see any bumps, see if we see any peaks that would be consistent with a graviton. That's exactly what we've done here. In red is our prediction from the Standard Model, in black is the data, and these blue points are different heavy gravitons. Fortunately, we didn't find them, but it was a very fun search. This is exactly what I've been working on over the last year. And there's many other searches that we can do with bottom quarks. So it's really a fantastic tool for hunting for new signs of new physics. But that's what we did in 2012. In the second run of the LHC starting this year, we're going to have more energy, more data, more intensity. What that actually means is the probabilities for producing those very, very heavy particles, they actually increase. Something like a heavy Z boson might become 100, 10 or 100 times more likely to be produced than it was with the energies we were colliding in 2012. So here you can see what a very heavy 3.5 TeV Z boson, or Z boson-like particle, would look like if it was decaying to 2 top quarks. So this is a search that we're definitely going to be undertaking as soon as we have more data. But with more energy and more intensity, there's sometimes more complications. I didn't mention this before, but when we collide 2 bunches of 100 billion protons, sometimes more than 2 protons interact. In fact, on average, we have something like 15 to 20 different proton collisions each time we overlap those bunches. And that's exactly what we see here. We see 20 different collision vertices. Now you can imagine trying to search for those secondary vertices, those secondary points where particles were produced from bottom quarks, can be quite challenging in this environment. And in fact, we're going to be moving instead of from 20, but up to 40 different collisions per second, or different collisions per bunch crossing in the next years. So how can we improve our ability to find those secondary vertices? Well, here's our system. This is the picture we saw before, our 3 layers of our detector. Now, there's 2 things you can notice about this. One is as these cones of uncertainty move away from the detector towards the collision point, they spread out. And 2, we also saw that as we shrink those red dots, we get more precise cones, smaller cones, more precise measurements of the trajectory. So if we add a new detector closer to the beam pipe with smaller circles, more precise measurements, which we can do now, this technology is now 10 years newer than what we had produced in the first round of the LHC, or of the first time we produced Atlas. Suddenly we see that these cone sizes shrink. So we've gone from larger cones to smaller cones. We can more precisely measure the trajectory of all of those different particles. So that's exactly what we're doing with what's known as the insertable B layer, the IBL, a new layer of vertex pixel detectors. So here's our beam pipe here. It's about 3 centimeters in radius. Our first layer of our pixel detector, you can see here in gray. That's at about 5 centimeters away from where the beam is. And in that 2 centimeter slice, that 2 centimeter window between the beam pipe and the old layer and the first layer of the pixel detector, we're going to slide in this new layer of pixels. So you can see them here in green, extending down each of these squares as an individual pixel detector. And this is what it looks like kind of organized around the beam pipe here in pink. So this is kind of a schematic of what one of those structures holding all the different detectors are. These are these brown objects, the different detectors. And I won't show you just cartoons. This is what one of those detectors actually looks like. It's about 2 centimeters wide and 2 centimeters tall. This is the electronics that connects it to the outside world. And here in gray, that's the slab of silicon. If you look really closely, you can actually see the individual pixels. Now there's 32 of these organized on this kind of mechanical structure. And we mount those onto the beam pipe. And sometimes they let me in there too to help work on this detector. So I was working very heavily on actually testing, calibrating, and qualifying all of these detectors and before they were mounted onto the beam pipe. Now in 2014, we inserted that detector into the center of ATLAS, and although we don't have collisions, we can turn the detector on and wait for cosmic ray muons to stream down through the system. And you can see here a cosmic ray muon. These are the new 4 layers of pixel detector. The red points are where the muon has deposited energy, and you can see energy deposited right on that trajectory. And suddenly we have a 4th layer of pixel detectors that's working fantastically. So this is really going to help improve our ability to do bottom quark and bottom hadron physics in the next round of the LHC. So what are we going to be doing? Well, this is 2 charts showing the searches that we've done over the last years of the Large Hadron Collider, searching for extra dimensions, searching for black holes, new heavy top quarks, new heavy W bosons. Here, this is the searches that we've done for supersymmetry, if you've heard of supersymmetry. And in purple here, you can see all the different searches that were done with bottom quarks. Bottom quarks are really this ubiquitous tool, and we're going to be using it to search for all of these things again, and search for new theories, and search for all sorts of fundamental new physics that may arrive in the next few years. So, to summarize, there's many interesting things that interact with or decay to the bottom quark, and since they have a long lifetime, we can actually see them at the Large Hadron Collider. And once we can see them, we can use them to look for that new physics that might be decaying to or interacting with the bottom quark. And with more energy, more data, and new detectors, we'll be able to do that even better with run 2 of the LHC. So, thank you.
So, Michael, thank you very much. We have time for questions. Now, there are people on the 2 sides with microphones. So let me call on you, or Michael will call on you. Wait until you get the microphone to ask your question, and then it'll be on the videotape along with the answer. So questions, please. Here.
What determines the size of a bunch, and could it be smaller, giving you less interactions to worry about?
So actually, what determines the size of the bunch is the Large Hadron Collider itself. They have many of the magnets are actually designed for steering the bunches, but then right before we collide them, we actually squeeze them, and the bunches end up being about, so in length, they're a few centimeters long, and in radius, they end up being about 16 millionths of a meter. So that's about the third of the radius of a piece of human hair. So you actually want to squeeze them down very small so that we have a higher probability of colliding them. Now, since interesting things only happen 1 in a million, 1 in a billion times, the fact that we have 20 collisions is not such a big deal. It's not that we're going to be producing a lot of multiple interesting things at once. So as long as we work very hard to tell the difference between those extra collisions and the really hard, high-energy collision that produce something interesting, then it's not so big a deal for us. Yeah.
You had mentioned trying to avoid bias, and that meant not interacting with the other team at the LHC.
Mm-hmm.
I'm interested in what you personally had to do, like avoid them in the lunchroom, like not read their work. Like, what does it mean to not be biased?
How do we go about that? Well, we've got 2 of these major experiments that have these very large collaborations hunting for answers to big questions. It turns out when you build 2 experiments on the same collider, they're going to be competitive. So there's actually a pretty healthy competition between the 2. And although we're friends, each of the collaborations still wants to win, still wants to be the first one to find that particle. So in the end, it's actually that competition which drives kind of the hushed nature of the competition. But we also know that we shouldn't be talking to each other because we don't want to bias each other. So it's also very self-driven.
Now that we know the mass of the Higgs boson, what does that tell us? Does that give us some clues as to its new physics, or how did that help us now that we got its mass?
Yeah, so the mass of the Higgs boson is actually an important parameter for a lot of theories beyond the standard model, like supersymmetry. So depending on what that mass does, can determine often what a lot of the other aspects of the theory work like, or how well a theory works at all. Some theories, if the Higgs boson was too light or too heavy, would no longer be consistent with the rest of the data we've seen at the Large Hadron Collider in earlier experiments. So that mass, understanding that mass actually throws out a lot of theories that we would have had to search for otherwise.
So I'm going to use a technical term of you have a zillion detectors
You have a zillion, yes.
in this apparatus,
Yeah,
and there's going to be a certain failure rate
That's
of
right.
the detectors.
Yeah.
So you're going to you can calculate approximately how many have failed, but you don't know where they are.
we know exactly where they are.
Really? Okay.
Well, when a detector fails, it's no longer giving us any data.
Yeah, but your events are sparse. So how can you detect absence of an event versus no data?
No. The interesting events are sparse, but the events are happening 40 million times a second. So you have to monitor the background while you look for interesting events. And
okay.
with those 40 million events a second, you can survey the detector very thoroughly. But you know that's what requires the enormous team. Someone has to be responsible for every element to make sure it's working or not. I'm sorry for taking.
No problem. Yet to give you a bit more information, only in about, a pixel will only get a particle going through it about 1 in a million collisions, but we have 40 million a second, so. Yes.
Hi. So I actually worked on the Aleph experiment many years ago, and I remember from that our average detection rate was about 20 megabytes per second. We didn't have quite the data rate that you did, but that was a electron-positron collider, and the collisions were much prettier and simpler than yours. And I'm surprised that actually 300 megabytes per second is what you're getting. I would actually think it's even an order of magnitude larger. So this is a combination question. So A, is 300 megabytes really actually correct? And secondly is, do you have some significant online real-time processing that rejects a large fraction of that noise that is just the sort of the uninteresting stuff before it even gets to the offline processing?
Exactly. You answered the question with your second question. So our system, so although there's 40 million collisions per second, we only record 200 of them per second. So we throw out almost all the data because most of it, if only 1 in a million or 1 in a billion is producing something interesting, we actually can throw out most of those collisions, and that's exactly what we do. So we reduce the data rate, reduce the amount of data we record from 40 million to 200, and that reduces the output data rate dramatically. Yeah.
What was the LHC designed for upgradability, or was the insertable B layer basically a hack put onto the existing LHC?
I think that depends on who you ask. No, I think from the very beginning, these systems have always been designed, we always think about the next upgrade of the detector. These silicon detectors don't last forever. As we irradiate them longer and longer, they stop working over time. And in fact, in the mid-2020s, we're going to replace the entire pixel detector, the entire inner part of our detector. All those tracking systems will be replaced. So these detectors and systems are designed with upgrades in mind, yeah.
Are there any experimental predictions from string theory or competing theories, and are there plans to investigate that?
So that extra dimensional model I showed you there was actually motivated by string theory. There are not really direct experimental predictions for string theory as of yet, but something like that extra dimensional model is kind of inspired by all those extra dimensions of string theory. Well, what if we only had one that kind of acted like a string theory extra dimension? What would happen? Maybe.
Yeah, I would like to take this question. String theory isn't a specific model of nature. It's a context. It's a mathematical way of producing specific models. And many of these models have very different properties. So there's one kind of model where you have an extended fifth dimension that suggests the kind of things that Mike talked about in that case. There are other models where you have dark matter associated with the top quark, which Michael also talked about. So string theory is an underlying motivation for many of these searches. But the idea of testing string theory, that's much further off. We got to find the model first, and then we'll figure out how internally it works.
Earlier in the lecture, you used a phrase that was something like the carrier of force information, which I thought was interesting because I guess I was wondering whether you kind of look at all of it as information at some level.
Whether we look at it all as information.
Like everything that you're investigating, I guess, as equivalent to information.
I think in that context, what I meant was that the way in which, when we talk about particles pushing and pulling on each other with a force, what that means is that these force carriers are being sent back and forth. I don't know quite how to think about particles in general in terms of something like information theory, if that's what you're asking about. Yeah. Okay.
Is the infrequency of the interesting collisions because those collisions have to happen absolutely perfectly head-on, or is there some other reason for why they are so infrequent despite so many collisions taking place?
Well, partially yes, because we're colliding protons and they're made up of smaller quarks, and those quarks carry some fraction of the energy. So not every time when they collide do they really produce collisions with all the energy. But that's not really the fundamental reason. That's a small piece of it. The fundamental reason is that all the physics that's going on in those collisions is governed by quantum mechanics. And quantum mechanics is inherently probabilistic. When you smash two particles together, you don't know what's going to happen. But you can compute the probability for the different kinds of things that will happen. And something like a Higgs boson has a very, very small probability.
So there's a few different experiments going on in this giant ring. How do you share the time between all of those experiments? And is there one particular hog of, the protons or?
So I guess we can go, well, it'll be a while before I get back. Actually, the beam crosses at every single one of those points all the time. The LHC provides 40 million collisions a second to all 4 of the experiments. So you just cross the beam at all the different points. Well, that's so essentially they're all, there's a lot of slides. We're almost there. Okay, so the answer is that we collide them, we collide at all 4 points at the same time because the 2 beams will come through and they kind of cross. And that crossing can be done just by steering with magnets. So all 4 experiments are constantly acquiring data. But for about a month a year, instead of providing proton collisions, they provide lead-lead collisions or lead-proton collisions. And that's what the ELISE experiment is especially excited about.
My name's Lee, and I'm a sensor guy, and I'm kind of curious about the sensors that you're putting in. And it looks like on the flex circuits that you were showing, the sensor is just a small area, and maybe 5 to 10% of the flex circuit area. And I'm wondering what percentage of the cylindrical detector area you have is actually sensing particles. How much are you missing and how much are you collecting?
So we've been using what's known as slim edge detectors. So the pixels go all the way out to the edge. I think the pixels go all the way out to, on the detectors currently, we have sensitive elements. So it's at the other side of the lecture now. I can try to get there if you want, but the detectors we have now are 2 centimeters by 6 centimeters, and only at the very outside, I think it's about 500 microns, I can check that number for you, is where there's actually no sensitive pixel detectors, and then there's maybe 5, so most of the area actually is active. I can't remember the exact fraction, but it's in the very high 90s. Then what we do is, because there's also edges where there are electronics, we actually overlap the detectors so that if there's a place where one of the detectors is not as sensitive, that it would have crossed a second detector's sensitive area. That's on both detectors, yeah. So, well, I don't think we'll quite get there. But yes, it's a very high fraction of a sensitive area. No, that's the master control chip, MCC.
Part of the physics is to find these neutrinos, which are missing particles. So So you have to see what recoils against them. If there's a dead space, you're in trouble. So great effort is taken in the engineering to cover all the spaces as much as possible with overlaps or with large pieces of silicon.
Sorry, I know, I understand. Yes, there's electronics above and below the sensor, and so it's the same active area. So a particle has to pass through actually one layer of electronics, then the sensor, and then another layer of electronics. But it's always going through the sensor.
I was disappointed to hear that you didn't pick up extra dimensions. Now, when you say something like that, or the failure to find supersymmetry was another big source of public disappointment, does that kill it, or are you hopeful? And I guess what I'm asking is, with these big kind of headline theories like supersymmetry or dark matter or extra dimensions and heavy gravitons, are you expecting, does the theory help you to be optimistic or pessimistic in the next era?
So absolutely. So I think one thing that's really fascinating about particle physics is that time and time again, we've looked at our data through the history of particle physics. We looked at our data, we saw things that didn't quite make sense or that our theory couldn't make sense of or couldn't predict. And then our theoretical physicists worked very hard to understand how we might fix that theory. So I even mentioned today, when we actually predicted the existence of the bottom quark well before we found it. And so that's kind of in the state we're in now. We have certain parts of our theory that we know we could understand better. We know there are some problems with. And in fact, that theory drives us, that those open questions drives us to understand that we expect this new physics to happen at about the energy of the collisions we're having here, that are operating here. This is kind of the sense of scale with which supersymmetry might exist. The next round of collisions is certainly sensitive to the same energy scale, the same kinds of theories of supersymmetry or extra dimensions. And it's exactly where our theory, our standard model, is telling us there might be new physics hiding, because something additional needs to be there for us to really understand what's going on at this kind of TeV scale. It's called the electroweak physics scale. And so our theory is really driving our ability to understand that this is where we're expecting new physics. And if it's not there, that's also a very interesting thing to understand too.
You mentioned that for like the past year, you worked on the graviton from different extra dimensions. Why is that project like so? I mean, I can see why, but I mean specifically, like, why are you so interested in that? And what macroscopic application are you expecting to see from that project? Like, what do you think we would eventually apply that to? I'm thinking just gravity and like, initially, sorry, I'm nervous.
No, thanks for the question. I think, understanding the fundamental structure of the universe is kind of a pursuit that we've gone about as humans since we've been around. Answering this, why gravity might have this individual structure may indeed one day help us understand how to travel in space, how black holes work better, how all the universe around us really works. And that's really the goal of what we're trying to do now, understand the universe around us. But this is really, in some sense, it's the pursuit of knowledge. It's interest for the pursuit of knowledge. And where that knowledge leads us, we don't know. When we discovered the X-ray, we didn't know it was going to be important, but now it's incredibly important. So what finding a fifth dimension will end up leading to in terms of application, I have no idea. But it certainly will be fascinating if we find it, and it certainly may open up new possibilities in the next 100 or 1,000 years.
What's the most interesting thing that you have found so far in that project that you're engaged in?
Well, I think that'd probably be the Higgs boson.
Okay, last question.
Eight 13 whence? Are you going to go? You're going to try to run at higher power level than the 13 giga electron volt?
13 trillion electron volts. We will probably we'll probably try to go to 14. That was the design of the accelerator. But it turns out you need to put a certain amount of energy into the magnets in order to bend them. And so we design our magnets to be able to operate with beams of certain energy. So we won't actually be able to just continue increasing the energy because the magnets that are bending the proton beam won't be strong enough to handle that. So yeah, probably this is where we'll stop now, and then in the future, a new collider may be produced that can go to higher energies.
Well, Michael, thank you very much.
Thank you. Thank you.